Hello, my name is Reut Levi, and today I'm going to talk about testing triangle freeness in the general model in graphs of Arboricity O of square root of n. A tester for triangle freeness with one-sided error has the following requirements. If G is triangle free, then the tester should accept with probability 1, and if G is epsilon far from being triangle free, according to some predetermined distance measure, then A rejects with probability at least 2/3. Alon, Fisher, and Krivulevich showed that in the dense graph model, it is possible to test triangle freeness with number of queries which is independent of the number of vertices in the graph, and Goldreich and Ron observed that in the bounded degree model, namely when the maximum degree is bounded by a constant, then it's possible to test triangle freeness in time which is linear in the proximity parameter epsilon. Alon, Kaufman, and Krivulevich and Ron studied the problem of testing triangle freeness in the general model. So in the general model, the density of the graph is unknown. It can range between 0 and n minus 1. The distance is measured with respect to the actual number of edges, which we denote by m. And we say that G is epsilon far from being triangle free if more than epsilon m edges should be removed from the graph in order to make it triangle free. Both vertex pair and neighbor queries are allowed. Vertex pair query is a pair ij, and the oracle answers yes if and only if there is an edge between vertex I and vertex j. Neighbor queries, we have a pair v, I, and the oracle returns the ith neighbor of the vertex v, if such a neighbor exists, and otherwise it returns some kind of special symbol. So as I mentioned previously, Alon, Kaufman, Krivulevich, and Ron studied the problem of testing triangle freeness in the general model. And they have several upper bounds and lower bounds. And they show that the upper bounds, they provided sublinear upper bounds for almost the entire range of the parameters. And the upper bounds they obtained are at most quadratic in the lower bounds. However, they have tight results only in two special cases, either when the maximum degree is of the same order of the average degree and the average degree is at most square root of n, or when the average degree is constant. Gugelman obtained improved lower bounds for some ranges of the average degree, and also Rust obtained improved upper bounds for some ranges of for the average degree. And the figure that you see is the figure that describes the lower bounds of Alon et al. And the upper bounds. So the green line describes the upper bound and the upper bounds, and the red line describes the lower bounds. So in order to describe our result, we need to define what is the arboricity of a graph. So the arboricity of a graph is the minimum number of forests into which the edges of the graph can be partitioned. In the figure, we see a graph that has arboricity 3 because we can cover all the edges of this graph using 3 forests, the red one, the green one, and the blue one. Roughly speaking, the arboricity of the graph is the maximum density of overall subgraphs. Formally, the density of a graph G can also be defined as the maximum over all p between 1 and n of m p over p minus 1, where mp is the maximum number of edges in a subgraph of G over p vertices. So before I describe our results, we need some notation. So n is the number of vertices, m is the number of edges, gamma denotes the arboricity of the graph G, and d bar is the average degree of the graph G. So our upper bound has expected running time and query complexity, which is O tilde of gamma over d bar plus gamma. So when the average degree is greater than 1, the complexity is the same, is up to polylogarithmic factors, is the same as the arboricity. And as in previous work, n, m, and epsilon are parameters of the problem, but gamma is not a parameter. We also show that this upper bound is tight in the following sense. For every arboricity which is bounded by square root of n, there exists some feasible m such that indeed the obtained query complexity is tight. Namely, we need gamma over the average degree plus gamma queries in order to test triangle freeness in the general model. And when I say feasible m, this is because m is bounded above by n times the arboricity and below by the arboricity to the power of 2. So in fact, the lower bound is even stronger in the sense that as long as the arboricity is bounded by square root of n, then for every feasible m, the lower bound is tight as long as m is at most n, or at least the arboricity to the power of 3. And in particular, it is tight as long as the arboricity is bounded by n to the power of 1/3. And when it is not tight, then the upper bound is O of the arboricity, and the lower bound is gamma of the arboricity to the power of 2/3 in the worst case. So let's see some more motivating example for our result. So let's consider sparse graphs in which the average degree is constant. So the upper bound of Vallon et al. In this regime is tight, is essentially tight, the upper bound of square root of n. And in our upper bound in this case is O tilde of the arboricity. And it gives better bounds when the arboricity is little o of square root of n. And it is always as good as the upper bound of Vallon et al. Since in sparse graphs, the arboricity is bounded by square root of n. Another example, consider a graph in which the arboricity equals the average degree, which equals theta of n to the power of 1/5. So in this case, we do not require any bound on the maximum degree. In fact, the maximum degree can be theta of n, even when the arboricity is constant. So in this regime, the upper bound of Vallon et al. Gave the best result so far, and it was order of n to the power of 3/5, unless the maximum degree equals the average degree, while our upper bound gives order of n to the power of 1/5. And in general, it cannot be worse than the upper bound of Vallon et al. Since in this regime, the arboricity is bounded by order of n to the power of 3/5 of Yes, okay. So, and in more generally, for any average degree between 1 and n to the power of 2/5, the upper bound of Ballon et al. Of square root of the number of edges was previously best known. And in this range, our upper bound is always at least as good and could be much better depending on the arboricity. Okay, so Eden, Ron, and Seshadri approximate the number of the k-clicks in the graph, and in their algorithm, the arboricity is a parameter of the problem. And in fact, there are other algorithms that are related to our work that require the upper bound on the arboricity as a parameter. So there is another work by Eden et al. In which they estimated degree moments, and another work by Eden et al. Which they sample edges almost uniformly, given the arboricity of the graph as a parameter. Okay, so let's talk about the algorithm for testing triangle freeness. So we begin with the naive approach that doesn't work, and then we see how we make it work. So we know that if a graph G is epsilon far from being triangle free, then there are many edge disjoint triangles in the graph. In fact, specifically, there are omega of epsilon m edge disjoint triangles in the graph G. So if we could sample an edge uniformly from the graph G, then with probability at least epsilon, we would sample an edge UV such that this edge is on some triangle, and if we reveal the neighbors of U and the neighbors of V, then we would see an intersection between these two sets, and we could reject the graph because we have a witness that the graph is not triangle free. So the problem with this naive approach is that we don't know how to efficiently sample edges uniformly from a graph, from a general graph. And the other problem with this approach is that either U or V can have high degree. So just revealing the neighborhood of these vertices might require too many queries. So let's begin with the first issue of how we can sample edges almost uniformly. Okay, so we can sample vertices uniformly at random, but we cannot sample edges uniformly at random if the degrees if the degrees of the vertices have a high variability. So what can we do in this case? If we knew the arboricity of the graph, then we could sample edges almost uniformly by making a O tilde of gamma over the average degree queries per edge that we want to sample. So what can we do if we do not know the arboricity? As I told you, the arboricity is not a parameter of the algorithm. So we need a couple of definitions in order to describe our algorithm. So for a threshold T, we define by HT of G the set of heavy vertices, namely all vertices that have degree at least T. And we define the graph HG, T to be the graph G after we remove all the edges in which both endpoints belong to heavy vertices. So let's see an example. In this example, the blue vertices are light vertices, namely vertices in which the degree is strictly less than T, and the red vertices are vertices in which the degree is at least T. So these are the red vertices are the heavy vertices, and we remove only the edges between the heavy vertices, namely the edges in which that are colored in red in the figure. So edges between heavy and light vertices are not removed. Okay, so why we are interested in this graph? Because we can sample edges almost uniformly from this graph. So we can sample vertices almost uniformly by making from the graph HG, T by making O of T over the average degree graph queries per edge that we want to sample, assuming the number of edges in this graph is not very small compared to the number of edges in the original graph G. So the sampling is then very easy. You just pick a random vertex V and pick a random index between 1 and T. And if the degree of V is at most T, namely if V is a blue vertex, is a light vertex, and it has a jth neighbor, then we return this edge. If it has a jth neighbor U, then we return the edge U, comma V. And we repeat this until we find an edge that satisfies these two conditions. And this happens in expectation after after we make O of T over the average degree queries. Okay, so we can sample edges uniformly from HG, T. But why this graph is helpful? So it is helpful because the number, if we consider the graph HG, the arboricity over epsilon, then in this graph, the number of edges is at least 1 minus epsilon times m. Namely, we do not remove too many edges from the original graph. So if the original graph was epsilon far, let's say 2 epsilon far from being triangle free, then HG, gamma over epsilon is also epsilon far from being triangle free, and therefore it has many edge disjoint triangles. The other observation that we need is that every triangle in this graph has an edge where at least one edge, in which both endpoints have degree, which is at most gamma over epsilon. And therefore, if we sample this edge, then we can reveal the neighborhood of both endpoints, because both endpoints are light. Therefore, if we knew the arboricity, then we could sample edges almost uniformly from this graph HG, gamma over epsilon, and test triangle freeness as follows. We would sample theta 1 over epsilon edges from this graph almost uniformly, and then check if both endpoints are light, then we would reveal the neighborhood of both endpoints and see if there is an intersection. Okay, but we do not know the parameter, we do not know the arboricity. So this leads to talking about the parameter gamma star. So since gamma is unknown, we consider a different parameter, which we call the effective arboricity. So the effective arboricity is the minimum gamma star such that the number of edges in HG, gamma star over epsilon is at least m minus c times epsilon m, where c is some absolute constant. So in other words, we look for the minimum gamma star such that we do not remove too many edges from the graph G when we switch to HG, gamma star over epsilon. Okay, so we show that gamma star, it's a simple observation that gamma star is bounded by O of the arboricity, and in fact it could be much smaller. And what we want is some kind of an approximation of gamma star. So we could obtain such an approximation if we could approximate the number of edges in the graph A, G, T. So this is exactly what we are doing. So in order to do so, we consider the graph DG, T, which is a directed version of the graph HG, T, in which the edges are oriented from light vertices to heavy vertices. And if both endpoints are light, then we break ties according to the idea. So given the graph, so how do we estimate the number of edges in the graph H? We just sample R, which is theta of T, which is the threshold on the degree, over the average degree of G over epsilon squared times delta vertices, where delta is the confidence parameter. So we sample this many vertices uniformly at random from the graph. And then for each such vertex, we just sample a random neighbor of this vertex. And we check if the edge between VI and UI is oriented from VI to UI. In this case, we set the variable yi to be 1, and otherwise we set it to be 0. And xi is just yi times the degree of vi over t. And then the estimate for the number of edges is just the number of vertices in the graph G, which is also the number of vertices in the graph H, times t, which is the threshold, times the average value of xi. And why is this estimates the number of edges in H? So we note that yi is just an indicator variable for the event that the edge vi ui is oriented from ui to vi. And therefore, the expected value of t times xi is the average out degree of H. Since xi is independent random variables ranging between 0 and 1, then we get by the multiplicative Chernoff bound that x is concentrated around the expectation, and that the expectation of x is exactly the number of edges in H. Okay, so in high level, the algorithm for testing triangle freeness first approximates the effective arboricity, and then set the threshold t to be this approximation over epsilon. Then it just samples 1 over epsilon random edges, almost uniformly at random from this graph H, and then checks if both endpoints are light. Then it rejects if then it reveals the neighborhood of each vertex of each endpoint, and rejects only if it sees a witness for rejection, namely that there is an intersection between these neighborhoods. If in all checks we do not see a witness for rejection, then we accept. So as I told you, this result is tight in some sense for graphs in arboricity, which is bounded by square root of n. It is tight in the strong sense as long as the average degree is constant, and we show this by a simple heating argument. And the lower bound for the other range of parameters is in the adaptation of the lower bound of Alon et al. Okay, so the open questions are: 1, can we show strong lower bounds for the entire range of M as long as the arboricity is bounded by square root of n? And the more interesting question is, what is the right parameter for testing for graphs which have arboricity which is greater than square root of n? Thank you very much for your attention.